difficulties. That presentation wasn't on the computer, so Stephen copied it from, emailed it from his phone.
I remoted it into my work machine, pulled it into my Gmail account, sent it here, got the voice verification, signed in, downloaded it, and now it's here.
This is the 21st century.
Yes,
Absolutely.
Right, so my name is Stephen Loftus Mercer, Principal Architect for LabVIEW R&D.
Jeff Kodosky, co-founder, author of LabVIEW.
These sorts of things. And this year, we're going to be presenting a new feature we've been working on that we've called Malleable VIs. So I'm going to let Jeff go ahead and start this.
So a little bit of history, just for the trivia folks among you. This was an experiment that I started many years ago. Called it Macros. It was built on X nodes, and it was a hidden feature. It's been a hidden feature for a long time. And but due to an interesting oversight, examples were shipped on the Macintosh distribution for many years. Last year we turned it live for everybody, but it was still a kind of a pioneering version experiment, still built on X nodes. This year it's been completely re-implemented using other technology that exists inside of LabVIEW, so it's a lot more robust and performant and has a lot fewer caveats associated with it. So, what is a malleable VI? So, in the simplest pragmatic terms, it's just a VI with the extension .vim. And basically it's that easy to create. You can go to the new menu and select new malleable VI, or you can take a regular VI and just change its extension to .vim. All right. We actually ship some malleable VIs in LabVIEW 2017. And they're on the various palettes. And the clue that they're malleable VIs as opposed to primitives is that the color has a little darker background in it. And but if you pop up on them, open them up, you can see how they're constructed inside. They look like a sub-VI. So, what do we do with malleable VI? We use the VI that you create with the VIM extension as a template. And when you drop it on the diagram, we create an instance VI that's hidden from that template. Then when you wire up to it, we modify the instance VI to have the types of the inputs that you wired up. Let the type propagation proceed to say what the types of the outputs are, and then propagate those on the following VI's diagram. And when you run this, run your VI, we will compile it first, and during the compilation of it, we will inline that instance VI. So, for those of you with old CS background, you might recognize that's kind of what macros did in older days. So there's a few restrictions that we have when you make one of these things. All the controls and indicators on the front panel have to be connected to the connector pane, and all their corresponding terminals have to be at the top level of the diagram, because we're basically removing those and just connecting the wires when we inline it. And so when you go to run it, there's no front panel associated with it. It's just a snippet of code that's been inlined. And you have to configure it to inline. So here's a simple example of a malleable VI. And this is kind of the one that got us started on all of this. I noticed in the idea exchange this idea for, they wanted to have a delay ability, be able to delay the data flow on a given wire. It was suggested have 800 kudos on it, and but the response was, oh, well, we can't do it. And
To be clear, I wrote that response.
and I said, oh, of course you can do it. It's real simple. It's just a macro at the time. And I shot off my mouth and showed an example online on the forum. Here's how you do it using macros. What's a macro? Oh yeah, you've got to turn it on.
To be clear, I found out about it from the lava post.
That's when we decided, okay, this really does have merit. Let's get it to work right, and so on, which led us to here. Anyway, so this is the simple example. I have the use case is I want to be able to put this node and wire up to it and have a delay that says delay the data flow by some amount. So it's real simple to implement if you were just doing it on your diagram. Put a sequence structure around a timer and run the wire through it, and that will delay that signal by that amount of time. But you don't want to put that snippet of code everywhere. It's a pain in the neck, and then you have to rip it out. But if you could do it as a sub-VI, that would be pretty good, inline sub-VI. But then if you have to make a version for every different data type, it's ridiculous. So what happens with our malleable VI process is we use that original template that just had variant in and out, and we create an instance VI. And when you wire the string up to the input, it changes the input of the instance to a string, propagates string on the diagram, so it comes out as a string output. We change the instance VI output to have that, and then the rest of the top-level diagram type props just fine. And then when we compile, we inline that bit of scripted code that it says there. It's actually no longer using scripting, it's just using our inlining capability. Okay, so that's a simple example. Here's another one. This is a simple version of one that actually appears on the palette for incrementing the value in an array. So my template or my malleable VI definition says I've got a 1D array, use an in-place element structure to index that array and increment the indexed element and output it. And so now when I go to use it, what types can I wire up to it? Basically, any type I can wire up to it is a, let's go back one, it is anything that can be wired, a 1D array of anything that can be wired up to an increment function, the increment function. So it could be a simple number, it could be, in this case, a cluster of numeric, of a floating point and an integer, and so whatever wires up to the plus is legal to wire up to my VI. But if I wire up something inappropriate, I'll get broken wire. Well, what do you do in this case? You can actually pop up on the instance and select create, what does it say?
Convert instance VI to real VI.
Yes, something nice and short.
Convert instance VI to real VI.
Yes. And then it shows you the instance VI that it created. In this case, for the top one, it created an instance VI that had a string array in and out, and when you index that, it has a broken wire going to the increment. And so when we see that the instance VI doesn't propagate properly, it ends up with a type prop error, we go back and say, all right, go restore the default data types on the instance and let the wires in the caller break. That's how we signal that there's an error inside. Actually, I think we want to do a demo at this point. You were going to show some, because that takes us into another dimension. This is awful cozy.
here. Examples. APIs. Here. Move my microphone over a little bit. So this is the shipping example that we've included for folks to look through. And what we're showing off here in this first piece is just several of the malleable VIs that we are shipping with LabVIEW. So let's take a look at the sort 2D array VI, which is a long sought after function in LabVIEW. Most of us have written this at some point for some sort of table data display. This one is capable of deciding whether you want to sort by column or row, and then which indices do you want to sort by. We've made it, so you pass in an array of strings, or I can pull that out, shove in and make it an array of integers, and we can see this output type shifts over to integer immediately. So you can see it's pretty responsive, not a whole lot of delay there in all the type prop and everything, and it's regenerating that down there. And we've also done some things where I can get rid of that single index, and I can wire up an entire array of indices, and that's propagating across that diagram as well. So as long as the block diagram, whatever that block diagram is doing, is capable of accepting the type, it works. Same thing down here with the shuffle 1D array. Now we can open these things up, and the block diagram, we've written it. You can write this using any data type that you want to use. We've written them using variant as a way of signaling we expect just about any type to be able to go through here. But as long as you pick one type that makes for a passing run arrow, that is what sets the baseline for this is a valid malleable VI, and then thereafter anything else that the callers will be able to follow from there. If we have some sort of broken wire on this diagram, then on the caller, it's going to say, hey, I'm not currently propagating the types. I need you to go fix the sub-VI. So it is aware of these things as sub-VIs. They do update as you modify the templates. There's a complete tie between them. They keep things connected. If you ever want to see a list of all of them, you can use QuickDrop, type .vim, and because the names are broken out, you'll see these are the malleable VIs that we shipped in the pallets. There's a couple of utility functions, numbered enum, stall data flow, and this is value changed. And then there's 5 useful array functions, several of which have been used for at various points. I know a lot of people have asked me for shuffle 1D array when you're writing test programs where you want to shuffle the data and send it through in various 1,000 monkeys testing. Sort 2D array is the other big one that gets asked for when you're trying to view data sets. They're pretty simple to create. You go in, new ... You'll find it, new malleable VI. We use the 4 colors here to represent the different data types of LabVIEW, so that's kind of our running glyph. And there you go. It's got a .vim file extension, nothing special. And from there, I just start wiring things up. It immediately breaks because it says, hey, this controller indicator is not on the connector pane. And they have to be for malleables. So I can connect it up. Now we're good. And I just keep writing a VI. So I'm not going to go too much further here because you guys have written VIs, or I'm not sure why you're at this presentation. Quick and easy. Put that together. I can put that on the connector pane, and now it's available to be dropped and used for different type flow. The types flow across the same way we've always done data flow, and we compute the new type, and that's how it works out. So you can end up with a VI that is as polymorphic as we can make our primitives. You can take these guys, nest one inside the other, so you can composite the functions. They don't actually work recursively because they're inline functions, and that can lead to an infinite stack. We've got some ideas where we might be able to work that part out, but at the moment that's not there. But they do composite very nicely. So we've got some people during the beta who are creating whole libraries of things. How many of you work on FPGA? So if you've got any fixed point math libraries, you can write it once for all your fixed point types. Your array manipulations, those work out really nice. Clusters, I usually advise anybody who's trying to do generic operations in clusters to convert them all over to LabVIEW classes. But after 10 years, I know some of you are just really resistant, and this will help those of you who haven't converted over. So those are the big cases that we expect the malleables to be used for.
So maybe we should ask for any questions at this point. We have some more info to show you, but any?
In terms of restricting the front panel terminals to only be certain ones, what was the logic behind having to force all terminals to be malleable?
Having to force versus getting to be.
So if you want to have an input, say, be an integer and only an integer, one way to do that, and we'll talk more about this as we go along, is to make sure that on the inside you wire it to something that only takes an integer, and then that forces it to be an integer. It won't accept anything else or break the wire. So you don't force it to be what you put on the panel, you programmatically force it to be
So we didn't see, and we still don't, even after a couple of years of field testing on this, a reason to take the C# route of explicitly stating these are the types I'm going to vary into, or to provide some sort of front panel calculus. The limitations on the types come from the limitations that you program in by how you use the data. So, as I say, it follows from data flow. If the type is able to flow through, why would we not want to let it flow through? It has a default type. You can set that up how you wish so that people can easily create controls and indicators from it. But once you've decided that this is a VI that is going to flex with its environment, then let it flex with its environment. That's basically what we've seen as the greatest utility.
I think we're going to have an answer to your question on the next example. So, anything else? So it's pretty easy, right? Being able to create one VI that works for many types, and as Stephen said, as polymorphic as our primitives, makes it nicer. Yeah.
So what about like complicated data types of like a cluster of different things? The case is you've got multiple huge state machines. And you've got they're all defined by like 3 different enums. You have 3 different state machines in your block diagram. To be able to use one of these to handle all 3 different types.
So something like a
like a cluster with an enum and a variant is how we define your that's the data type that you use.
Yeah. So I just built this cluster of a class and an integer, and it propagates across of an object and an integer. It propagates it across just fine. When I do create of the indicator. Yes, it works out. Assuming you actually put in a type that can be sorted. That's the problem. That's not a sortable data type. And that's where the type limitations come from, is it's computing that from the block diagram. If there's no comparison basis, then it doesn't work out. But whatever, it can accept, yes, the types, it's open for all of the data types of LabVIEW.
So if you imagine you built the sub-VI and you put specific control types on it, and it did its type propagation and it came out okay. If you change your front panel control to another type and it propagates through the diagram just fine, and maybe an output type changes and you change its type as well, then that's a good example of a malleable VI. That type that you change is the one that can adapt. And so by default, we say all the inputs are adaptable, but if you want to restrict them, you have a way to restrict them. And so the way this is working is, like Steve said, we didn't want to invent a new kind of calculus to describe legal types. We wanted to employ duck typing. Has anybody heard the term duck typing. You know, if it walks like a duck, quacks like a duck, must be a duck. In the type propagation, if it propagates through, then it's a legal type. If it doesn't, it's not. So that's the philosophy we took on this. Okay, if we go back to our presentation, we'll show you one more thing that is under construction. You might have a situation where the code I would like to do for each type is slightly different. And so now, how would you do that inside of a Malleable VI? So, okay, this is the old version. This is all, got everything all on one slide. Good. We don't have to change slides. So, we have a new structure. It's called a type specialization structure. It's very much like the diagram disable structure. You use that to comment out sections of code or have two versions and you can enable one and disable the other. This structure has multiple frames, and the idea is that for the types that you've wired up, we try to propagate it on the first frame, and if it succeeds, we accept that as the valid frame, and the rest are ignored. If it doesn't propagate properly on the first frame, it tries the second frame. If that one propagates okay, it's the accepted diagram, and the rest are ignored. If it gets to the end, and none of them have propagated successfully, it picks the last one, which has a type propagation error in it, so then the Malleable VI containing this structure will have an error and the wires will be broken. So here's an example of a simple VI that says, take anything and produce a string. So in the first frame, the first column over there, the first top frame, I have a string wired up, and that string propagates through, and it's accepted, and that frame is used, and the others are ignored. In the second column here, I have a folder wired up to an instance of that Malleable VI. That path that goes over, when it encounters the first frame, it's broken, and so it ignores that one, or declines that one, and then the second frame has a path to string conversion in it, and so that's accepted, and that's the valid frame. The last one is ignored. In the third column here, I'm wiring up a string array, and so the string array is declined in the first frame, declined in the second frame. The third frame accepts an array of strings and will concatenate them with a line feed between, and then output the string. Yeah. So that frame is accepted. How did I get the zero frame, the first frame there, to reject a path? If I just had the wire straight across, a path would propagate straight across. But I really want to force it onto the second frame that accepts a path. So basically, I want to have something in the first frame that will cause a type propagation error if the input is not a string. So it's going to reject everything that is not a string. And that's that little function we have called types must match. It's a built-in primitive that has no runtime impact. All it therefore is to compare the two inputs to say, are they the same type at type propagation time? And if they are, everything's fine. If they're not, it causes an error, which is enough to reject the frame of the type specialization structure that it's in.
It's at this point that I want to jump in and stress that these are under construction, and I may have already broken binary compatibility with 2018. Just saying.
Yeah, so that we have some additional ideas of where to go and how to make this structure easier, how to put in more kinds of type primitives that allow you to specify not only that this has to be a particular type, but that it has to be related to another. For instance, one input must be an array of the other, or some other complex relationships. So in general, what we would like to be able to do is use all of the type parsing functions that we have in LabVIEW and have those run, do constant folded computations, so they run during type prop, and then they have no impact on runtime. Which I should point out that in those examples, the frame that's selected is the only one that's compiled. The rest are ignored. So there's no runtime overhead for having this kind of polymorphic behavior of a malleable VI.
So some of you saw when we opened this debug debug right VIM.
Nothing's showing up with that.
Ah.
I have a question after that.
Yeah,
Does this type function work on classes?
on classes.
Yes.
Yes, it does. And there's more to be done there.
There's actually we're actually going to have an entire set of, for lack of a better term, type algebra primitives for different types of comparisons. So this particular one does exact match, and it works on any of the data types, and there will be other variations on that for near misses and such like that, coercible, that sort of thing. This debug log directory, some of you know that Darren Nattinger and I like to ship VIs that we don't necessarily have time to send through the proper process and get them all documented and polished and everything. But when they're really important to us, because they're so helpful, we ship them anyway. So this debug log is a VI that everyone in this room has probably written at some point. When I run it, it simply gives me a dialogue that has the various events of what occurred in what order. And this one is written in such a way that it will take any of the LabVIEW data types. So I can get the integer, then the information about the ref num, and all that. But this one, the reason I opened it up is it's one of the places where we've used the this type structure. So I can start off here, and this one is the one that knows how to write a string. Okay, strings are good. But I can go through and I'm basically handling all the different types in LabVIEW with a final case at the end that says if all else fails, write out the XML. So. VILib utility debug log.
Install hidden gems, you'll get it.
Yeah. So, back to the presentation here.
We have a few questions.
Yes. Up there, good. All right. So, Jeff, how do malleable VIs differ from poly VIs and X nodes?
Yeah, well, I think they're more flexible than poly VIs and a lot simpler than X nodes. But X nodes is a hidden feature, so maybe a lot of you don't know about that either.
All right. Will malleable VIs be available in LabVIEW and XG?
Yes, but not right away. The type specialization structure, which is an experimental thing that we're still under construction in LabVIEW, it'll take a little longer.
They have a really nice data pane. We have, malleable VIs. There's things for all of the versions. Can I nest one malleable VI inside another?
Yes.
That one's easy.
Yep.
Can I put a malleable VI inside a poly VI?
No. And you can't do this because we don't have a way to put a fixed type signature on top of it because it uses duck typing. So the poly VI is another mechanism that says, I'm going to search down the list of VIs until I find one that has the type signature that I'm wired up to. So since we can't do that, It's not possible.
Yeah, basically, when you try to look at it, it's like it'll always pick the VIM because the VIM says, hey, I can accept that type. How can I make a VIM that accepts only unsigned integers?
So this is back to Norm's question, and if you want to accept any unsigned integer, then you would use the type specialization structure and have a case per uint type. So uint 8, 16, 32, 64. When we eventually have some of these more sophisticated type comparison primitives that Steve was talking about, there'll be one that says any uint.
What happens if I save for previous?
Well, the instance VIs will become real sub-VIs, so your application should still work, but you won't have the flexibility to be able to have it adapt to types beyond that.
Okay. Keep going here. Will a VIM work in LabVIEW 2016 using the Xnode implementation?
Maybe. You can take the VIM, save it for previous, and put the VIM extension on, try to load it into 2016, and it may work. But the type specialization structure isn't back there, so you can't use that. And there's some caveats associated with usage of classes and so on. So I wouldn't guarantee it for sure, and it may not be worth trying to do this back in 2016.
There is a reason we don't release features when they're still in prototype stage. Can I have a recursive malleable VI?
No, not yet. This is an interesting research topic because, if you're going to do recursion at type prop time, you've got to make sure that you do converge. Otherwise, it'll crash LabVIEW very unceremoniously. So it's.
So basically, if you need to have a custom function that can unroll an array of cluster of array of cluster of array of array of array of cluster, you're going to have to do some hand coding at the moment to catch each of those cases. We're trying to figure out how to flip back and forth between a set of VIs to slowly unroll a type in a way that we can guarantee a base case. Are there any other questions?
Can you convert existing VIs to polymorphic VIs to malleable VIs?
We don't have a tool for converting a poly VI per se, but you could take one of, assuming the block diagrams are the same, and this is the big caveat, is you're still going to use poly VIs if the block diagrams are actually radically different. But assuming all the block diagrams are the same and you just did save as, pick one of the instances and do save as.vim and mark it as inline, and you're done.
You might even be able to take the multiple very different implementations in a poly VI and put them in different frames of a type specialization.
When you get those.
When you get those.
Yes, exactly.
And then I'll script the answer for you.
Yeah.
In the event that you do, say for previous of 2016, and you use that malleable VI as both a string and an integer, which did have to get saved as, or just save it with different file names?
So if you save the VIM, it'll just save the VIM just like it would do any other sub-VI, whatever type was on your VIM. But each instance of it, if you've used it in several places, then you'll get a separate sub-VI for each of those places, and it'll be customized to the type it's wired up.
There's a couple of VIs. So we thought long and hard about this. So the type specialization structure is not in the palettes. However, we wanted people to be able to play with it who knew about it. So it appears on the block diagrams of some of the shipping VIs, and those VIs are not password protected. There's a giant comment next to it that says this is not a stable feature. We stabilized it and proved it out for the specific VIs that we were using, and we've checked its cases. There may be edge cases on it that don't work out, which is part of why it's not in the 2017. But we were confident enough in it that we could rely on it for builds. So it's exposed there, so you can copy it off of any of those block diagrams. So look at a lot of the array functions. It appears there in a couple of places, or the debug log.
No, you can tell your friends.
You can tell your friends.
I mean, I'm always of the opinion that, you know, if we warn you and you want to try it out and give us feedback, that's great. It'll advance the state of the art that much faster. But if you want to stay away from the warning, that's okay too.
Or you could delete all the warnings and then tell your enemies.
I like that plan. I have some folks in there. How do we best give you feedback on that? Usually your absenteers aren't updated on the latest and greatest.
Yeah, well, you can always email me or Stephen.
You can post private messages to us through the NI.com forums. That generally works. If you want to have a longer discussion,
Start at the red on the form.
yeah, you know, the regular LabVIEW forums, you know, you can flag us by name, and you know, we'll usually notice where someone will escalate it to us if it goes too long. But generally, that sort of conversation works out pretty well.
You create a malleable VI where type propagation works when you wire it up, but there is coercion happening inside the malleable VI. Will that show up where you get an indication that that's happening from the outside, or it'll allow that?
I didn't quite hear it.
So the question was, if you wire the outside of the malleable VI, let's say you wire with a double, and inside it works, but inside there's a coercion to integer. Is there any indication on the outside that the coercion is occurring inside? No, there's not. And we thought long and hard about elevating that coercion dot and trying to pull it up. And it turns out that there are some very strange cases where that's either hard to compute or where we didn't want to elevate it. For example, the number to enum, where we were explicitly writing a coercion bullet, and we didn't want to promote the coercion dot that we were computing. So we've gone back and forth on that, and what's probably going to end up happening is some form of formal primitive when we start having the type algebra and stuff, something that says, you know, accept it as a coercion, and that one will know how to promote up. But at this point, it just accepts in.
Can you put a TSS in a TSS?
Yes,
Probably so. I haven't tried it, but
I have.
okay. Good. You always like to try those.
Yeah, actually, I stuck it in the corner, so it's a corner case. No point in being in LabVIEW R&D if you can't make bad puns.
Has there been much playing around with property nodes of different types and casting and trying to have the structure itself so you don't have to have multiple nested case structures to handle different types of like VI server references specifically? Does that make sense? So if you've got one VI server reference, you're not exactly sure what type it is, and then trying to figure out what type it is and execute the code only based off of what type it is.
Right. So
Property node will automatically coerce.
that should work. I actually haven't tried it directly with the ref nums, but I've tried it with all the LabVIEW classes. So the property nodes do coerce there. Now, the methods, like the actual sub-VI nodes for a LabVIEW class, don't coerce yet. Keep your software subscription program up to date.
What were some of those edge cases or caveats with using this with classes?
No, it was with using the old version with classes. The X nodes and classes fight each other.
Yeah, X nodes, classes don't get along well. They don't play together well.
One of them thinks it's in charge of type prop, and the other one is wrong. The one question nobody has asked is why we called them malleable VIs. I did kind of expect that, you know, malleable, it's a term meaning, you know, moldable, flexible, metal, and it makes sense because we have malleable functions now to go with our ductile wires. And we know they're ductile because they can be drawn as a wire.
These are terrible shows.
I told you we'd be here all week.
Well, that's all we have to present. So if there aren't any other questions, we'll hang around here for a while, chat. Ask. Thank you.
Thank you.